We're going to talk about hybridization models and why do we even have hybridization models. So let's talk about carbon. Carbon atomic number is 6 and 12. Right here is the mass of the most abundant isotope. We know that this is the number of protons in the nucleus, but also the number of electrons in the neutral atom. So I'm going to write the electron configuration. And so 2 electrons in the 1s orbital, 2 in the 2s, so I have 4. And now in the p's orbital, and here I have 3, I have 2 electrons. So now let's draw the configuration doing the energy diagram. So I have here the 1s level, then the 2s level of energy. And close to that, I'm going to draw 3 lines. These are the 2 p's, so x, y, z. Now I'm going to put the electrons following the rules that we know. So Aufbau principle says that we need to start filling the electrons from the bottom up. So 1 here and 1 here. And I'm using here Pauli's exclusion principle, so that they need to have the 4, at least the spin different. When 2 electrons cannot have the 4 quantum numbers the same. So in them I need to put 6, so 1 here in the next, so it's 4. And here I need to use Hans rule. And here, because these 3 orbitals are degenerate, I put 1 here and 1 here. I have my 4 electrons. But it turns out that this is a configuration, say, of a carbon atom. But that does not explain why carbon can make molecules such as methane and have 4 bonds. Not only 4 bonds, but they are identical in length and they are in a very symmetric structure in a tetrahedral form. And these are the angles. So that cannot explain. I just have to have full orbitals, and so I could explain molecules with, say, 2 bonds, but not that. So to do that, then we have the hybridization model. What we're doing next is we're going to promote 1 electron from here. They're very close in energy. So I'm going to draw another configuration. And this time, because I moved that 1 electron up, I have, this is the 1s, the 2s, and again, the p's, the 3p orbitals, and putting my electrons, I'm going to do 1, 2, and then here I have only 1 and 3, because remember, I moved one of those over here. Now, the configuration here, you can explain that carbon can make 4 bonds, but you cannot explain a geometry such as the one in methane having 4 bonds identical. So for that, we now are going to make our model is we're going to mix 1 orbital 2s in this 3 p's, and we're going to make hybrid orbitals. In orbitals, we can think of those, they are mathematical functions, so we can create new mathematical functions, those hybrids. So this here, from 4 atomic orbitals, this is in the 3 p's. We're going to mix to create 4 hybrid orbitals, hybrid atomic orbitals. And because we're going to be mixing the s and this 3 p's, well, the name of that would be sp3 orbitals. So 1 of the s and 3 of the p's. That's the name of those orbitals. Now the diagram, and I'm going to erase, what do I erase? Let's see, this here. We have already worked that part. So what would be now my diagram? Well, now I have, this is still here, the 1s, and I will have 1, 2, 3, and 4 lines. And this is the 4 sp3 orbitals, all of those. And now when I put my electrons, now I have 1, 2, and then 4, orbitals here that are half full, so ampere electrons. This model is able to explain the geometry of methane because here you have 4 bonds to hydrogen, each of these bonds having 1 electron, say, coming from carbon and 1 from the hydrogen. So here I can represent the bonding with hydrogen by adding these electrons coming from the hydrogen. And that will be what is in methane. So all of those are identical, same level of energy, same geometry. So at the length here of all the bonds is identical, and the geometry is perfectly symmetrical. So that model, the sp3 hybridization model, reproduces the experiment. So that is experimental that we have this type of structure. Methane does exist. Okay, we're going to talk about other hybridization models in the next video.